Welcome to Grandmaster Series. I'm your host Jay, and in this special episode, we'll delve into intriguing world of building robust recommendation system. I'm incredibly excited about our discussion today, as we will be engaging with some of the world's leading experts in data science. Together, we will analyze the auto multi-objective recommender system challenge, gaining valuable insights into the development of a top-tier recommender system. Before we dive in, I'd like to mention a couple of things. Any material or resources that are publicly accessible and pertain to today's discussion will be linked in the description below for your convenience. And don't forget to subscribe to our channel to stay in the loop for upcoming videos in the Grandmaster series. Now, without a further ado, allow me to introduce our esteemed panel. First off, we have Benedict. He's a deep learning engineer at NVIDIA working on recommender system. He holds a MS in data science from Columbia University. And previously, he developed recommender system for a German e-commerce company. Next, we have Chris, a senior data scientist at NVIDIA. Chris has a PhD in mathematics and computational science with a thesis on optimizing parallel processing. He's also a 4x Kaggle Grandmaster. Next, we have Kazuki, a senior data scientist at NVIDIA. He's been a Kaggle competition grandmaster since 2019, and he's had 6 top 2 competition rankings. Next, we have Gilberto, better known as Jiba, currently a senior data scientist at NVIDIA. Prior to this role, he worked at various companies, including Petrobras, Airbnb, and Siemens. Jiba has held number 1 position at Kaggle for more than 2 years. Next, we have Theo, a senior deep learning data scientist at NVIDIA. Theo holds a master's in computer science and recently joined NVIDIA late last year. He's also a 3x Kaggle Grandmaster. In this episode, Chris will kick us off and he'll provide a bit of a background on the competition. Now that the stage is set, I'd like to hand it over to Chris and I'll be back in the end for the Q&A session. Chris, over to you.
Thanks, Jay. We got an exciting episode of the Grandmaster Series today. First, we'll introduce ourselves. In today's series, we're going to be, it's exciting because we'll be presenting 2 top solutions in Kaggle's auto recommender system competition. First, we'll introduce ourselves, then we'll introduce the competition, then we'll introduce general solutions to recommender system problems. Next, we'll specifically show our second place solution. We'll show our third place solution, and we'll end with questions and answers. In today's episode, you'll be hearing from 4 Kaggle Grandmasters of NVIDIA, KGMon. Chris, you'll be hearing from Kazuki, known as Onodero at Kaggle. Gilberto, known as Jiba at Kaggle. And Teo, you'll also be hearing from Benedict, who works on NVIDIA's Merlin recommender system team. We're very happy with the results. We worked really hard in Kaggle's auto recommender system competition. You could see the results here. So the 5 of us formed 2 different teams and we worked independently. Jiba, Benedict, myself, and Teo were on one team. We came in 3rd place, and Kazuki teamed up with some other Kagglers and came in 2nd place. This was an incredible competitive competition. There was 2,587 teams from around the world competing. The competition lasted for 3 months. Most teams are experts in the field, and you could see from the final scores that the final ranking was determined by just the 3rd and 4th decimal place. So it was an incredibly close race. And we're super excited to have finished well, and we're super excited to share our solutions with you today. So what is the task in this competition? So Auto is the largest German online store. And in this competition, we have to predict what users will do in the future. So given a user's history of engagements, we are given 3 engagements: when they click items, when they put items in their cart, and when they order items. Our task is then predict what they will do in the future. So what will they click next? Which items will they put in their cart for the remainder of the week? And which items will they purchase for the remainder of the week? To build our model, we were given trained data containing 13 million unique users. Each of them, we were given 4 weeks of their history, which totaled 213 million engagements, each with a timestamp. And there were 1.8 million unique items. So it was a very large problem. Once we build our models, we were then asked to predict unseen test data, which was the next week in the future. We were predicting 3 targets, as I said, clicks, carts, and orders, and the metric was recall at 20. And pictured here is just one example user. In this example, this user engaged with 7 items in their history. You could see they clicked 3 items, they put 2 items in their cart, and they purchased 2 items. And we would need to predict what they're going to do next. All right, now Benedict will introduce us to some recommender system solutions.
So thanks, Chris. So I will talk about typical Rexus model, like it's a 2-stage model. And normally you build recommender system 2-stage model, and I will explain why that is the case. Like as Chris said, we have like 1.8 million items, and we have like 12 million users. So if you score for every user all the items, this gets pretty expensive and pretty complicated, and it's like really a complex problem. So what normally you do in a recommender system is you have like millions of items, and you build a first stage model, which we call candidate generations. And then you want to narrow this down to like 1,000 potential candidates. So these are like the most likely candidates. And then you build the actually model, or the Reranker or ranking model we call, which then scores these 1,000 items to produce the final predictions, like the 20. And the advantage is, like in the second stage, you can build a lot of features, really complicated models, and you can build a like heavy problem, because you only need to score like 1,000 or even 100 items in our case, and get your final recommendations like 20. And this is then a really efficient solution, building like a pipeline. Thanks, Chris. Back to you.
Right. So as Benedict said, a typical very effective solution is doing the 2 stages. So in the first stage, we generate candidates. And there's many ways to do it, but a common way is to use co-visitation matrices. So there's 1.8 million items. So, how can we narrow it down to maybe 1,000 per user? So first, it's motivated by an observation. When we look at the history of many users, we actually notice that a lot of clicks occur together. So here you see, for example, when a user clicks item 5391, they frequently clicked next 5392. Or after a user clicks item 7321, they frequently put item 6543 in their cart. So after observing that items frequently occur in pairs, this can help us whittle down possible candidates for a user, because we can look at their history and use this idea of pairs. So the idea of pairs is computed using something called a co-visitation matrix. So what we actually do is we're going to build a matrix, and we're going to count up how many times every single pair of IDs or items are seen in a user history. So on the y-axis, we have all the product IDs, and on the x-axis, we have all the product IDs, and each element in the matrix is how many times those 2 items occurred together within a user history. Now, there's 1.8 million items, so this matrix is going to have 3.2 trillion elements. So it's far too large to actually build the entire matrix, and most of it is zeros anyway. It's highly sparse. So what we actually do is we actually just compute the top n items that will be engaged with in pairing with one specific item. So pictured here in the middle of the slide is the top n list for item 4. So using the item 4 column from the co-visitation matrix, we see that when a user clicks item 4, they're most likely to additionally click item 7, and they're second most likely to click item 1, then item 5, item 0, and item 3. So for each product ID, we can actually, by looking at all of the pairings and user histories, we can actually figure out what additional items most commonly are paired with the first item. All right, so once we have all these top-end dictionaries for all the items, how do we use them? Oops, I jumped ahead of myself. First, the question is, how do we create them? So this is a lot of work, right? Because we already mentioned that there's 3 trillion different pairs. So to actually count up how many times pairs occur is a lot of work. So we can do this. We can make this. We can speed up the process by using GPU, and specifically using the Rapids library QDF. We can compute this very efficiently. And this is how we do it. So pictured on the left is what the data frame looks like. So we have one column indicating the user, and then the column aid are the items that they engaged with. TS is the timestamp. Type is whether it's a click, a cart, or an order. So the way we create the pairs is we can actually take the data frame and merge it onto itself using the column of user. When we do that, within each user, we end up getting all the combinations. So let's look at this example here. So on the left, we see that user 0 in their history has items 1, 2, and 3. When we merge this on itself in the middle, we get the resulting data frame in the middle, and we see the original single column of aid. There's now 2 columns, aid X and aid Y, because of the merge. And we have all the pairings. So we see 1 with 1, 1 with 2, 1 with 3. We see 2 with 1, 2 with 2, 2 with 3, right? So the middle data frame now contains every single possible pairing from the train data. And this merge is incredibly fast because we're using QDF. And then what we want to do is, once we have all the pairings, we can then determine which pairings are important to us. So maybe, for example, we think consecutive pairs are the most important, or maybe we think items that are clicked within 1 hour of each other, or maybe items where both items were a purchase. So based on what we think is important, we add a new column called weight, and that is added in the middle data frame on the far right. So that's based on what we believe is important. And then after we have that new column weight on the far right, we group by and aggregate over all of the pairs, and we sum the weights. So on that final data frame on the right, we now actually have all of the pairs and a weight indicating essentially how often they occur together. So we can, sort this data frame and then extract our top 10 lists. All right, so once we have all of these top 10 dictionaries, how do we use them? Well, what is the top-end dictionary? So top-end dictionary tells us that if a user clicks this item, then we often see these other items in pairing. So in this example here, the colored rectangles are a user's history. And then we can take a top-end dictionary and apply it to every item in a user's history. So if you look to the far left, the last item, the oldest item that this user clicked was item 1001, and the top end dictionary for item 1001 says when this happens, we'll frequently see a pairing with item 2344, item 4321, and item 7654. So in this example, this is just the top 3 dictionary, and the user has 8 items in their history. So we've now got a list of 24 possible items. But you can imagine if a user has 100 items in their history, and we use, say, a top 50 or a top 100 dictionary, we can easily have, say, 10,000 items. And that's using just one co-visitation matrix. We can build a variety of different co-visitation matrices, different top-end dictionaries, and apply each one separately and get 10,000, 20,000, 30,000 of these items. And then we see that a bunch of items repeat themselves. So from all of these items, we can just pick which ones were the most common. Maybe take the most common 100 or 200. And now you've seen, using this technique called co-visitation matrix, for each user, starting with 1.8 million items, we've now narrowed it down to just a couple hundred per user. That's stage 1. And now Benedict is going to talk about stage 2.
Thank you, Chris. So as I mentioned before, we built a two-stage model, and Chris introduced like one of the most important features is like co-visitation metrics. And here we see what is the result of it. So this is an example data frame where you have like the first column is the user, or like it was the session. And then we have the items. These are like generated by our candidate generation process. And for example, a candidate generation process was the co-visitation matrices Chris mentioned. And now we have the opportunity to add a lot of additional features. This could be like only user-specific features, for example, the length of a session, how many items were there, what was the day, the hour, or like item-related features. It could be like how popular were they, or like what kind of category or other item features they have. And then interaction features. This would be, for example, the scores from your co-visitation metrics or from other models or from other like processes. And then finally, you have your target. This is your last column. These examples, we create like 100 rows for each user, like 100 candidates. And then we add all of these features to them. And then we can finally train a gradient boosted tree Reranker to predict the score of like each user item pair. If you go to the next slide. Yeah, this is like an example for how to train our Reranker. You see on the right side the code. It's pretty simple. We have our candidates, and this is like really a large data frame. Like if you have 100 items for all 10 million users, you get up to like, oh, a lot, 100, a billion. And then you get the candidates. The X train is like your features, then your target, you create your D metrics, and finally you train your XGBoost model. You can have different objectives there, like the classical binary pointwise. Then you have the listwise Reranker or pairwise Reranker. And finally, you can accelerate this all on GPUs. This was super important for us because the super large data frame to train your XGBoost model would take a lot of time otherwise. And yeah, you can have alternative re-ranking models. Like I might take something up front, but it could be like CatBoost or neural networks. But yeah, there's like a lot of opportunities. Moving on to like the first solution from Katsuki.
Thank you, Benedict. Here is our second place pipeline. Our second place solution consists of 3 parts. And today I will focus on feature engineering in first part and ensemble in third part. Next slide. Yeah, since co-visitation matrix was already explained, so I will now briefly explain just the difference. After merging same session of the left tables, I generated count features and aggregated the different features by AID X, type X, AID Y, and type Y in the right table. The difference features, let's say TSDiff, are the difference of TSX and TSY. Next slide. Yes. After merging candidate data frame and co-visitation data frame, I aggregated all features by session and candidate AID. In the beginning, I generated only one type Y features, e.g. older models only use type Y equal order. After that, I added other type Y since we have 3 kinds of type Y. LV improved from 0.595 to 599 by adding other 2 kinds of type Y. This means we have to know other behavior, i.e. how the AID is clicked and added to the cart even at the time of order. Next slide. Yeah, this is first stage prediction features. Remember, my models consists of second stages. So in second stage, I can use first stage prediction. Next slide. I generated two types of features here. In left table, the primary key is session ID and candidate AID. And the right table is the result of first stage prediction. And the first feature is merge prediction from first stage by candidate AID. And second one is merge prediction from first stage by session event AID, and then aggregate by candidate AID. As I said, the primary key is session ID and the candidate AID, so I needed to aggregate them. Next slide. So yeah, this is pseudo event features. I augmented session event AID using first stage prediction. The below is example of using top 2 candidate as pseudo event. With this method, I could generate other features, e.g. co-visitation feature can be applied more since session event was augmented. The left table is actual event, and the middle table is the result of first stage. Then in this example, I choose top 2. So in session 1 and click, I can choose candidate AID A and C because the probability is 0.9, 0.6. This A and C is top 2. So in right table, as you can see, their event is only A and C click, but I could augment it in like right table. So I could get a lot of events. With this method, I can augment other features. Okay, next slide. Now I will explain modeling part. I used Reranker of XGBoost and CatBoost for orders and cards. For click, I used only XGBoost binary with binary logistic. Pairwise of CatBoost is better than XGBoost in cards model, and it gave us diversity even in orders. Moreover, first stage is only XGBoost. You can see the difference between first stage XGBoost and the second stage XGBoost. All categories improved more than 0.001, not only CB but also LB. This is because of the features I just explained before: first stage prediction features and the pseudo event features. Next slide. Yeah, now I will explain Rust branding part. Our best branding ratio is 1:1. As the table shows, my teammates' order and cards model are better than my model. But my quick model is better than my teammates' one. Both our LV score 0.6 0.02, but we could reach 0.04 with blending. Why is that? Because our candidates were more than half different. So it means more than 10 candidates are different. So this diversity could reach 0.604. This is the end of my part.
Thanks, Kazuki. We'll now hear from Teo and Jibo, who will discuss the third place solution.
Okay, nice. Thanks, Kazuki. Now it's time to present our third place pipeline and what we did with the co-visitation matrix and how we generate features from that, right? Okay, and this slide is showing our modeling strategy in 4 blocks. So basically we have co-visitation matrix, candidates generation, feature engineering, and finally candidates re-ranking, okay? So I prefer to split the slide into 2 parts, the 2 left blocks that are related with candidate generation stage and the 2 right blocks related with re-ranking the candidate stage, okay? So starting from the leftmost block, the idea here is create item candidates based in previous items clicked or purchased by users in the user history, right? So basically, we use all the user history to create what we call that co-visitation matrices. And of course, every time you create the co-visitation matrix, you are splitting the data by folds to avoid overfitting on our validation folds, okay? So actually, these co-visitation matrices are not probabilities. It could be transformed probabilities, but actually it looks like more the popularity of any given item to be clicked or purchased given all the other items that appears in the same user histories. So it's very related with recommendation, and there are infinite ways to calculate the co-visitation matrix. And exploring this diversity is one of the keys to build strong models. Okay, also we calculate many different co-visitation matrix using different strategies. We can apply the results to each item in the user history using different weights and have a list of possible candidates, right? That's the idea. So we limited our candidate list to 75 item candidates per user session, right? And interesting to note here is that submitting only these candidates from the candidates generation algorithms using co-visitation matrix is enough to score top 15 in leaderboard. So this co-visitation matrix can be very simple and powerful approach for any recommender system. Okay, after these 2 initial blocks, we have a list of candidate items per user or session. Now it's time to make better predictions because the metric is calculated using only 20 item candidates in this competition. And we have a list of much more candidates. So what we do is called candidates re-ranking algorithm. We create a new data set with all the combinations of user ID and the 75 candidates. So this new data set is 75 times larger than the original number of sessions or users. And then to any row that represents an item that the user has purchased or added to cart, we label as 1 and all the rest as 0. Okay, this way we transform the data set to be able to be solved by a simple binary classification approach. And this is one of the keys of our solution. Once you have this new data set, the candidates and the labels, we just need to create more features using all the information from the items in the user history and mixing with the co-visitation matrix results. But one example, we can merge the co-visitation matrix scores for each item candidate in the user history. Or we can tell how many times the user clicked in the item before, or even create a rank of user history based in the any of the co-visitation matrix, and then rank each item candidates. The Possibilities to create new features using co-visitation matrix and item history here are almost endless. After we have a bunch of new features added to this ranking data set, we run GBDT algorithms to rank the item candidates for each user. Why GBDT? Because they are non-linear, they are fast to train on GPUs, and very powerful algorithms out of the box without doing any special pre-processing. We tried deep learning algorithms as well, but no one was so accurate at GBDT for this task. This is basically our final solution, and that scored top 3 in the final leaderboard. Next slide, please. Okay, the co-visitation matrix algorithm is very powerful and customizable and can be used in multiple ways to generate better item candidates or to generate multiple features for the re-ranking. Okay, this is clear. So when talking about creating different co-visitation matrix, we must think how to process the data to generate the item pairs in the co-visitation matrix. For example, we can calculate one co-visitation matrix considering pairs of items given only items seen before the specific item timestamp, or we can calculate other co-visitation matrix taking account both directions of time for each item before and after the timestamp of the item. Also, we can consider using a window of any items before or after any given item, or maybe using a filter to filter only items purchased before or added to cart before. So there are many ways to consider when building co-visitation matrix, and the possibilities are infinite as well. But which one is the best? The ones that gives the best recall on the item candidates list, or the best map metric in the ranking algorithm? So a lot of experimentation is necessary here. I recommend try anything you can imagine, use your imagination. But we ended using 7 strategies here in our solution. We can see on this slide, strategies to build the co-visitation matrix, right? But we have many different co-visitation matrix, and we need to apply the results to the sessions in order to create features for the re-ranking, right? This is the next stage. So we applied the co-visitation matrix using nine different approaches in the data set. Basically, we can use our user item history to apply the co-visitation matrix and have the candidates or features to the data set. But we found that using more strategies to apply the co-visitation matrix in the data set, in the user history, tends to score higher, right? So we use some variations like using only cards or ordered items in the user history to apply the co-visitation matrix, or using only the last item in the history, or even apply the last hour items in the session. There, you can imagine infinite ways to apply the co-visitation matrix results in the user history in order to generate features. And diversity is the key here. Using different ways usually tends to boost the scores. Next slide, please. Another idea about feature engineering is to use factorization machine embeddings. On the left side of the slide, I show a data set we created to train a factorization machine model based on the last 9 items in the user history, plus a feature describing the hour of the week. So the idea about factorization machine is not using the predictions, but using the item embedding table generated after training this model, right? The item embedding table can represent each item as a vector. So similar items have similar vectors, and this makes it possible to use algorithms like nearest neighbor to search for similar items using the embeddings and calculating the distance of similar embeddings in user, for example, in the user session history. It adds even more diversity when creating features to the ranking data set. But also we can use embeddings to create better candidates in the candidate generation step. And based on the cosinus similarity of all items in the session and the candidates, plus adding some linear weights based in the order of appearance of the items in the session, we can derive statistical metrics like mean, minimum, maximum, standard deviation of item cosine similarity and use that information as feature in the dataset as well. Okay, so there are many ideas, infinite ways. We just try to explain better what we did in our third place approach here. Now I will pass the baton to Theo to talk more about modeling. Theo?
Thank you, Jiba. So we'll be discussing a few ideas, and first one being how you want to handle the data. So as mentioned before, we have 1 month of data for training, and the next week is going to be kept hidden. It's a test set, and only Kaggle has it. And what you want to do usually is use the last week of your training data for training and validating models. And you do so using a cross-validation scheme. And whereas on the other end, you're going to keep the first 3 weeks for building features, and that's what we call the history. And to avoid leakage, you're going to truncate sessions that overlap between the first 3 weeks and the last week, the fourth week. And one simple improvement idea is going to be, instead of simply truncating, you're going to be splitting sessions into two. And the beginning is going to be used for history, whereas the end of the session, which is going to be on week 4, you can use it for training. Another improvement idea is going to be to improve your history using part of the week 4 data. And namely, we want to use the training data from week 4, not the validation data, to improve our features. Next slide, please. Then I'm going to dive into some of our pipelines. The first one being mine. The first step is going to be quite straightforward. You're going to want to split the data into 4s. And make sure to split by session, otherwise you're going to be linking information. And on top of that, I use the extra training session tricks I just mentioned. So next we want to train models, but there's a bit of an issue because you're going to have a lot of samples. And to improve efficiency, downsampling is going to be needed. And we use 2 ways to reduce data size. The first one is to remove session with nothing to predict. And that's quite natural, because if there is no history to predict afterwards, then there is no signal. And the other idea is to tackle class imbalance by downsampling the negatives. And actually, we wanted to keep between 20 and 50% of negatives, and this was more than enough to capture the signal, and it significantly improved performances as well. So moving on, we can now start training models, and what I did actually is optimize the parameters with Optuna, and then train the XGBoost classifier. And I do it for every fold independently, which you may think will take ages. But actually, on GPU, it's quite fast. Using Rapid XGBoost, you can train the full pipeline in only a few hours, whereas on CPUs, it would take days. And last step, which once again is going to be super fast on GPU, is inference. And you want to look into tools such as Rapid CUDF or Forest Inference. Next slide, please. Next pipeline is going to be Benedict's. And Benedict's added a few interesting stuff that we did not consider with Jiba and I. And first one is going to be using deep learning models. Benedict is an expert in recommender system and very familiar with how to do end-to-end recommender system with deep learning. And he built a GRU pipeline as well as a transformer for like pipeline. And these 2 models provided great scores that you can use as features in addition to the ones that are more classical. And by classical features, I mean co-visitation matrices, as well as word-to-vec embeddings, and other session and candidate features. So that's the first idea. And the other great idea is to leverage that the targets are hierarchical. And what I mean by that is, in order to buy an item, you first need to add it to your cart. And to add it to your cart, you need to click on it. And therefore, the probability that an item is added to cart depends on the probability that the item is clicked. So to incorporate that, it uses the click probabilities as input for the cart model and the cart and click probability as input for the order model. Next slide, please. And finally, quickly describe how we ensemble models. And for each of our pipeline, which already scored in the top 20, we retrieve the 20 prediction and use the average of the rankings as the final rank. And thanks to the diversity and to the fact of having three different pipelines and 4 individuals in our team, we could achieve third place. Next. Yeah, I think this is the last slide, so move on to questions and answer.
All right. That was truly a fascinating discussion. Thank you to all of the panelists for sharing deep insight from the competition. I hope our audience found this session as enlightening as I did. Now we are into the Q&A segment of our episode, and our panelists will answer and enlighten us further about building successful recommender systems. The first question is, how many GPUs did you use? Do you have a preference for working on a GPU-enabled desktop, cloud, or on cluster?
Thanks for the question. I'm happy to answer. So my pipeline would run on a single GPU, but it still would, like, the competition was over 1.5 months. And of course, I always built on top of previous results. But if I would want to run it end to end, it would still take over 24 hours running everything on the GPU. So like this would really take long without a GPU. So what I normally do is I have maybe 1 or 2 or 3 workers, each with a GPU, and can run some of the scripts in parallel. But yeah, it would fit into a single GPU, but you can speed it up by running a lot of things in parallel on multiple GPUs. And about the environment, so I prefer cloud because it's easy to scale up and scale down these kind of problems. So you can spin up multiple workers, each one for an hour, and then you have a lot of amazing results, and then you can analyze them. But yeah, desktop would be as fine as well, or cluster.
Okay. Thank you, Benedict. The second question is, how do you come up with all the co-visitation matrices?
I'll be happy to answer this. I spent a lot of time building co-visitation matrices, and in the end, I came up with 20 that were each very effective. So if you remember, the idea of a co-visitation matrix is that we're just counting up pairs, pairs of items that occur simultaneously in user histories. So basically, I just count up every kind of pair I can think of. So basically, you have to define what a pair means, right? So for instance, a pair can just be items that are engaged with consecutively. So basically right after one another. So that's the definition of a pair. And then you go through every single user's history and you count up those. Or I say, 2 items that were engaged with within a 1-hour window. Different idea, different bunch of pairs, count those up. Or, items of different types. There's click, there's cart, and order. So I said, okay, the first item is going to be anything. And then the second item will be only a purchase. So they engage with, so that's a pair. So different pairs than before. Or I said, let's only look at users, that interact with the website in the morning, and then amongst those users make pairs. So basically, I just kept thinking of different ways of what a pair can be, and then I would just create the co-visitation matrices. And then what's really important is having a local validation. So I had a local validation which I could evaluate each idea. So I would get a new idea and I could compute a local score which would approximate the leaderboard score. So I went through maybe hundreds of different ideas, and then those 20 I found that when I sort of add them into the mix, they increased the score. So just trial and error and a variety of different ways you can define a pair.
Okay, thanks for the answer. Great approach and great ideas. Thanks for sharing. The third question is, can you discuss the most challenging aspect of this competition and how you overcame it?
Yes, I want to answer this question. I think inference was the most difficult part for me because there were many candidates for tests. So I needed a lot of system memory, GPU memory, and CPU. However, I overcame this problem by using many DJX. If I remember correctly, I was using 8 machine for inference, and without that machines, I think it takes more than a day for only inference.
Okay.
Thank you for the
Okay.
question. Yeah.
Yeah. Cool. Thank you, Kazuki. And we have a last question, which is, what was your team's approach to collaboration and how did you manage coordination during the competition?
Yeah, I can answer that. So I think the key idea when teaming up on Kaggle is to share ideas. And apart from that, you do whatever you want. But the way we tackle it is discuss a lot of ideas on Slack, like feature ideas. Chris had a lot of co-visitation ideas, co-visitation matrices ideas, which he shared and we reused. I myself had my own ideas for pipeline. And Benedict and Jiba shared a lot of features as well. And once IDs are selected, filtered, everyone tries to add them to his or her own pipeline. And in our case, keeping diversity in pipeline was very important because it boosted our score to top 3. So there's a trade-off between sharing everything and keeping a bit for yourself. And yeah, the approach we had by basically everyone has his own code and everybody shares the mind.
Okay, cool. Thank you for sharing the answer, Pugh. And thank you all the panelists for sharing their insight. And congratulations again for becoming the top 3 finalists for this competition. Before we wrap up, I'd like to remind everyone to subscribe to our channel to stay updated about our future episodes of the Grandmaster series. You can find any resources discussed today in the description below. Thank you all for joining us in this Grandmaster series episode. We are thrilled to have shared this journey into the world of data science and recommender system with you. Until next time, keep exploring, keep learning, and remember, with NVIDIA, you are always at the cutting edge of data science. Thank you.